Okay, we'll go ahead and get started. So we've finished Module 1 on communicating structure, really related to the different functional groups that carbon can have. So we're going to make the assumption again that every molecule we study has carbon and hydrogen, and any other element is called a heteroatom. And so now in Module 2, we're going to use spectroscopic methods to determine the presence of those different functional groups. So there's a lot of ways of communicating this stuff. There's the name of the functional group, what's the sort of minimum bonding pattern we need, and then how does that contribute overall to the physical properties of the molecule. So this module is called Structural Elucidation Using Spectroscopy. There's a little bit of math involved, addition, subtraction, division, that sort of thing. We're not going to get too terribly complex with the physics and the mathematical equations behind the methods that we learn in this module. I'll give you a conceptual sort of breakdown of what's happening when the light interacts with the compounds, but the physics of it, we're not going to focus too much on that. Really what we're interested in doing is how do we interpret data and how do we develop an intuition about what that data is telling us. And the reason this is important at this stage in the semester is we want to understand when a reaction can produce more than one thing, how do we differentiate those different compounds? So we're going to start off today with mass spectrometry. Then we'll get into infrared spectroscopy. Then you'll have your first exam for this module. And then the remainder of this module will focus on NMR spectroscopy. And really that's how we image molecules. So doctors and physicians use MRIs, that's magnetic resonance imaging, to take a picture of your body. And we use NMR to take a picture of a molecule. And these different methods tell us different things about the structure of the molecule. So now that we know the bonding patterns for the different functional groups, what are ways we can tell that they're in a molecule? And so the general method is spectroscopy, and that's the interaction of light with matter. So if you've taken physics, you've heard light described as either a wave or a particle. We're not going to get down into the nuance of that, but we need to understand that like what you perceive as light, like coming from the ceiling or from the sun, is just a small portion of light in the electromagnetic spectrum. So there are different wavelengths of light, and they all have different energies, and they interact with matter differently. So the light interacts with the matter, that causes some response that can be measured by an instrument. And based on the the energy of that light, it's going to tell us something different in each region. So the three main techniques, notice the wording of the first one. It says mass spectrometry. That's actually not based on light, so it doesn't use the word spectroscopy. Infrared or IR, and then NMR. And so those IR and NMR will interact with different parts of the molecule and give us signatures. So the point of this is we want to prove the structure of a compound with very high confidence. And in doing so, that allows us to reject any other possibilities or claims. So this is where I like to say we're kind of now in an open world, and we don't really want to commit ourselves too much to a formal sort of application of solving problems. We want to be pretty adept in how we think about things and make sure that the data kind of fits and doesn't we can't claim something in one part and then have it be rejected in another. So everything has to fit together and make sense. So if you've ever heard of the term metacognition, that means you're thinking about how you think. And again, sort of like with the Lewis dot rules, when you draw a structure, does every atom kind of obey the bonding pattern for that element? So if you draw a carbon with 5 bonds, you can say that that's got to be wrong. I'm doing something incorrect. So you need this feedback loop of, is this making sense? There's also a heuristic called perfect is the enemy of good enough. So you got to take that first step. You have to make some assumptions and just get moving and realize that it's an iterative process of, yeah, this part kind of fits so far, but I can't make sense of this. So I got to explore a little bit more and realize if you get on a path and it doesn't pan out to the correct answer, you can backtrack. So we can't really solve these things just front to start and be correct 100% all of the time. So the next one is Sutton's Law. So a reporter asked this bank robber, "Why do you rob banks?" And the response was, "That's where the money is." So was that the intent of the reporter or not? We don't know, but that's the simplest answer is I need money, then banks have it. And if you've heard of Occam's razor, this Woodward's aphorism as it's applied to pre-med students is when you hear hoofbeats, think of horses and not zebras. So whatever the data is telling you, don't try to imagine some very complex situation. Anyone watch House, Dr. House? So we're not doing these crazy differential diagnosis with these, very one-off diseases or anything. And as Hemingway says about the old man and the sea, all the symbolism is shit. The shark is a shark. The old man is an old man. So what in the simplest form is the data telling you? What do you know? How do you make the connection? Don't start imagining wild scenarios about things. And I think what you'll see over the next couple slides is a lot, but now we need to train you in figuring out how do you make these connections to arrive at something logical. And then when we do that, you'll start seeing some of the ambiguity that exists and what I think is the fun part of structural elucidation. So we're going to start with this problem. We're given a mass of 86. So we can think of that as 86 grams per mole. How do we determine the molecular formula for an alkane? So this relates to mass spectrometry, which is an instrument where you have a sample, you put it on there, it's going to give you a mass number. And we know already that if we're given a molecular formula, we can determine the molecular weight. So now we want to run that problem in reverse. We have a mass, how do we determine the molecular formula? So we have two facts here that we can use, and then we need to understand what those facts are telling us. So this, I'm going to use this nomenclature, M to Z is equal to 86, and I'll explain what that means over the subsequent slides. M is mass, Z is charge. But for our purposes, it's 86 grams per mole. And the other fact is it has to be an alkane. So we know that the general molecular formula for an alkane is CnH2n plus 2. So we really need to find out what N is. So we need to take that first step, and I think this is a challenging part for a lot of students, is you're like, I don't know where to begin. Well, I said every molecule has carbon and hydrogen. So carbon has a nominal mass of 12. So I'm going to use that term nominal mass. 12 and no decimals, just 12. So the first thing we can do is determine how many times does 12 go into 86. So this is, again, it's not telling us right now what N is. It's just giving us a place to start. And let me say, you know, in terms of teaching philosophies, other people will teach this different. There's another way you can do this that might be a little more straightforward, but I like this way. I think it teaches you a lot as a place to start, and then you can start making assumptions or iterations from there. So 86 divided by 12, what do we get? So let's say 7. If we do 8, what's wrong with 8? We're past 86, so that's our threshold. And there's probably going to be some questions about sig figs and rounding up or down. The only thing I can tell you is that just try it. We already know that we can't use 8 because 8 times 12 is past 86. So that right there is what we're going to toss that out. That's part of our intuition. So we start with 7. And now what we're going to do is backtrack and say 12 times 7 is what? What's that equal? 84. And then the H contribution is 86 minus 84. So we're going to use 7 as the carbon count. So that will result in C7H2. So does that make sense for the molecular formula for an alkane? So no. So it doesn't obey the 2n plus 2. Because it's an alkane, there's no degrees of unsaturation. So as practice, C7H2 would have how many degrees of unsaturation in it? What? 7? So I mentioned that because, like, if you wanted to practice, can you draw 7 carbons and 2 hydrogens with 7 degrees of unsaturation that obey the Lewis dot rules? So you can make a structural claim, but when you look at it, there's some red flags that should go off in your head that say, that's not a reasonable compound to exist. It obeys the Lewis dot stuff, but structurally it's kind of insane. So that was our first approximation. We can reject it because it doesn't match the alkane formula, so what do we do now? We go down to 6. So 12 times 6, where the 6 is now the n part, that gives us how much mass contribution of carbon to the 86 is that? 72? So that will result in C6H14. So does that now obey the alkane formula? So we can just verify that by plugging n into there, and we see we arrive at the same thing. If you ever watch any court TV, and you kind of see the prosecution, going after the defendant, they need to paint him in a box and say, this happened at this place, this time, blah, blah, blah. So we already rejected 8, we rejected 7, 6 seems to be the right thing, but let's put a box around it so that we know unambiguously it has to be C6H14. So let's drop down to 5 and understand why 5 is also unreasonable. So what is that, 60? So that does not make any sense, right? Because we already know from the alkane CnH2n plus 2, the maximum number of hydrogens for the n number of carbons is 2n plus 2. So 26 is way past that. So we've blocked in the C6H14. It has to be that. So in terms of answering this question, we've answered it. We've figured out a molecular formula, but within that molecular formula, there's still some ambiguity. it tells you the total number of carbon, the total number of hydrogen. We know the mass, but what it doesn't tell you any of the connectivity of the carbons or the hydrogens. So remember, when we were greater than a carbon 4 count, you can have linear and branched isomers. So mass spectrometry will give you a mass number, which you can then deconvolute into a formula. But that formula is not really telling you how any of those elements are connected. We get that information from IR and NMR. So as a practice, you can go and take this, see how many. You can draw one linear isomer, that's hexane, and then you can draw a bunch of branched isomers from that. So try to practice that. Any questions? Over here. What? In mass spectrometry nomenclature, M is mass, Z is charge. For the purposes of this class, Z is always going to be 1. So really, it's just mass. Yeah.
Can we use the arithmetic method to find the number of carbons here by multiplying n with 12 and then substituting it with 86?
So as I said, there's other ways to do this. Another one's called the rule of 13. You arrive at the same thing, maybe a little faster. But in my mind, this is a little bit more straightforward. The rule of 13 is basically you take carbon 12 plus hydrogen 1, that gives you 13. And then you kind of go through this same process. So I'll show you, after we look at an actual mass spectrum, because we started with what's the maximum number of carbons. I'll show you an equation where you get the exact number. So, as I said, carbon and hydrogen are always there. What about these other heteroatoms? So now we're going to look at an example where we can walk through the problem-solving things we need to figure out by shoving in some heteroatoms. And the example I want to use is testosterone, which is shown on the slide there. And you've probably heard of testosterone. It's a steroid. Steroids have this common sort of structural nucleus to them. Since we are talking about organic, which is primarily molecules, what are they used for? This is a hormone, and a hormone is a molecule in a living system that it's a signaling compound. It tells the process to start, to continue, or stop. So there's the structure. There are the choices for the molecular formula. What do you think? So let me point some things out in terms of, I don't know, just the pedagogy of learning. When you read a molecular formula, it's always C, then H, then the other elements. So when you're looking at those responses, you might be tempted to, oh shit, I got to start counting all those carbons. Well, there's a lot of them, right? So what's there the least of? Oxygen. So when you see the molecule, you see 1, 2 oxygens. So you can start eliminating responses based on that. So A can be eliminated because that says 3 oxygens. Now B, C, and D all have 2, so we don't have to worry about comparing the oxygens there, but you also don't really need to count the carbons or the hydrogens by looking at those 3 remaining responses. Can anyone tell me why? I mean, degrees of unsaturation, but I guess you could use that logic in terms of how the heteroatom affects the hydrogen count. What do you notice about the hydrogen counts? Two of them are odd. And oxygen does not affect hydrogen count, right? So you can't have an odd number of hydrogens. So it's got to be even. So you can arrive at C is the correct response for this one without even doing any of that C or H counting. And again, to reiterate that, the oxygen count does not affect this. So if we're going to reduce this down to just a CH count to determine degrees of unsaturation, overall the number of hydrogens has to be even. So again, that's part of the intuition. When you're looking at structures, you want to start seeing patterns like that. So we get C19H28O2. And I'm going to use this, again, this term nominal mass. And I'll explain the nuance of that as we look into the actual data. But just using the H equals 1, C equals 12, O equals 16. Take the proportions of those elements in the molecular formula, and what do you arrive at? So B, 288. Everyone got that? So again, we're just taking 19 times 12, 28 times 1, 2 times 16, add that together. So we have the structure. We can determine degrees of unsaturation by just the visual examination. And let's do it this way. How many pi bonds do we have? And if we wanted to, again, practice what we know, we could identify what they are. So that's a carbonyl. And that's an alkene. And then how many rings do we have? So we add that together and we get 6. So if you weren't given the structure and you just had the molecular formula, then you would have to use the kind of algorithm we talked about for that. So 2 pi bonds and 4 rings. So we have 6 degrees of unsaturation embedded in the molecular formula. So we said there were 2 oxygens, and what are the names of the functional groups those oxygens are a part of? I think I heard an A, secondary alcohol and a ketone. So again, when you're looking at really, we have carbon, carbon, carbon. There's all kinds of carbons, but what really stands out are the major functional groups that contain heteroatoms. So you look at their bonding patterns. So we know OH is an alcohol. We can then classify it by looking at the carbon bearing the OH. That has 1, 2 carbons, so it's secondary. This carbon has a pi bond to oxygen, it's a carbonyl. That carbon has a carbon and carbon attachment, so it's a ketone. And so now that we've identified alcohol and ketone, where we're going with this is with infrared spectroscopy. It is going to tell us that those bonding patterns are in this molecule. It says they're in there. It doesn't tell us exactly where they are. The connectivity is NMR spectroscopy. So we have to use all of these different techniques to get layers of the structure. So here is a mass spectrum. So there's the structural formula of testosterone, the molecular formula, molecular weight, or what I've been calling mass. And down here, what does all this stuff mean? So each type of spectra that we look at based on the technique is going to look very different. So when you see this, it should be kind of imprinted in your brain that that's a mass spectrum. So any 2D graph has an x and y axis. On the x-axis is m to z. That's the mass to charge ratio. Z is charge. So for our intent and purposes, we're going to assume Z is 1. If it's greater than 1, it gets a little bit more complicated beyond what we need to know in this class. But why is it charge? Again, I'm going to give you the cheap explanation of this technique. You have a compound that you're going to put into an instrument. The compound itself is neutral. There's no charge. In one variation, the compound gets hit with a beam of electrons. That is then going to form an intermediate that has a +1 charge. So there's the 1, and then the charge is plus. It's now an ion. The ion is then what gets detected at the back end of the instrument. So anything that you see as a red line that's coming off the x-axis is a signal. It's an ion. So mass spec detects ions, does not detect anything neutral. So we start at 0 mass. We increase in mass from left to right. Now, you'll see the heights of those red lines, those signals are different. The y-axis says relative intensity. I like to use the term abundance. So a couple things I want to point out on interpreting this, the most important things for us. So there's the chemical formula. You were able to determine what's the nominal mass. It was 288. So if we start at 0 and we march all the way up to 288, we see a line there. That signal that corresponds to that mass is called the parent. And it's given this nomenclature M. And then in square brackets, it has the plus. That indicates it's a positively charged ion. The parent ion is the mass that contains everything in the molecular formula. So those things are equivalent. That ion has everything in the structure because the mass is 288. Therefore, anything less than that mass is called a daughter ion. You have your compound, it's hit with some electrons, it forms an ion, it's fully intact. It's not happy because it has a positive charge on it, so it's high energy, which means it's going to do stuff to break apart, and that's called fragmentation. You have one thing, it breaks apart, you get these fragments. That's what every other red line on here is. It's a fragment of that parent, and they're called daughter ions.
Is that parent ion existing at the same time, or are these measurements taken at different moments?
So it's almost instantaneous. As soon as you shoot it on, like, I guess that's one thing you have to rationalize in your brain. It's like, I mean, it's so high energy and it wants to get to something more stable that it's like boom, boom, and you will see all these things at once. It's not like you see the parent and then 5 minutes later you see all these other fragments. There are fancier instruments called orbitraps, which is like a magnetic bottle where you can trap the parent. Then that parent, you hit it with different energy that will select out for different fragments. But again, that's a bit fancier for us. So I want you to also understand, see the height of that signal? If you draw a line over to the y-axis, so let's say about 80, the abundance of the parent is 80%. See this one right here at 100%? Notice the mass is obviously less than the parent, but that's the most abundant peak. It's called the base peak. The parent ion does not have to be the base peak. All that is saying that the parent is observed and then it fragments to this other thing that is more stable. It funnels into that bucket most often. Why does that happen? Again, we're not going to go into how things break apart, but it happens in a logical manner. And the way you interpret this stuff is you take 288, can't read that, let's say 124. 288 minus 124, what's the difference? The difference is something neutral that you're not seeing. Questions?
Is the parent ion losing or gaining anything in these process?
Structurally, the parent doesn't lose anything. And that's kind of what's hard to understand is the best way to think about it, you have your Lewis dot structure. it's getting hit with some form of energy, say like a beam of electrons, an electron bullet. All that's doing is knocking one electron out to form a plus ion. So at that point, you're not breaking any bonds or anything, you're just forming an ion. So remember, the parent is the mass with the intact molecular formula. The base peak is the most abundant ion. Yeah.
Do we have any idea which ions would be taken out to make the base peak?
I guess that's not really important for us. We just need to understand just that nomenclature. So the question now is, I gave you the structure of testosterone. You went through all the kind of questions from Module 1. What's the molecular formula? What's the weight? What are the functional groups? If we think of the problem this way, if I just gave you the mass of 288, could you come up with the formula of testosterone? And then from that formula, could you draw the structure? So you see it gets now increasingly more difficult, and there's a lot of ambiguity about that molecular formula. We can figure out degrees of unsaturation, but then how do we know it's 2 pi bonds and 4 rings?
So does that mean that basically we can really mainly just do that whenever it's an alkane?
So the question was, can we just do that whenever it's an alkane? And what we're going to spend the rest of this lecture on is what are some of the logical ways of approaching this to understand that there could be heteroatoms in there. So that's where we have to sort of do a little bit of assuming things to say, from the carbon and hydrogen mass contributions, is there stuff left over? And what could it belong to? So from 288, can we arrive at that? And I'm going to tell you, yes, we can. And the reason we can do this relies on, remember I said nominal masses, we were just using just the whole numbers for the atomic masses. Now we're going to start putting some decimal places after that. And the reason we're going to do that is because each element can have isotopes, and the ratio of those isotopes will allow us to drill down into a specific molecular formula. So we've used that word already, isotope. So with hydrogen, there's 3 isotopes. You have hydrogen itself. The next one's called deuterium, and then the one after that is tritium. So carbon is typically C12, but there's C13 and C14. So 12 to 13 to 14, that is telling you there's isotopes. So E is the element, A is the mass number, and then Z is the atomic number. So the difference between things is the number of neutrons, which is Z minus A. So you start adding these neutrons in, you get these isotopes that can be stable or long-lived. And then if you add too many, you get radioactive isotopes. So hydrogen, deuterium, tritium, C12, C13, C14. They exist. And they exist in different ratios. And that is what is important for this technique. So here's our periodic table of those elements that we're interested in to construct molecules here. So we have our Z, that's our atomic number there. So hydrogen, deuterium, tritium, this is how they're represented. So normally we just write H, we don't put the 1 there. Deuterium, you can say D or 2H. So that's superscripted number before the element is telling you it's an isotope. Notice now I've jacked up the number of decimal places here. So we're going out pretty far, and what that allows us to do is increase the accuracy for determining a molecular formula. The last column, see how it says percent abundance? Of the 3 hydrogen isotopes, hydrogen is 99.9885% abundant. So if you had some sample of all of these isotopes, that would be the main one. C12, C13, C14. C12 is 98.93. C13 is 1.07. See the difference between them is 1. And that C12 is about, I'm going to round, 1.1% abundant. So if you're thinking statistically how this relates to molecular formulas, you're going to get a threshold for any natural sample you have. One of those carbons is going to be C13 labeled. So we have nitrogen 14 and 15. So N14 is 99.6. A bunch of different oxygens. So the ones that are the building blocks for life are the stable ones. They're the most abundant. The next set are the halogens. Fluorine 19 is 100% abundant. That's kind of a sticky wicket that leads to some ambiguity about its presence or absence in a molecule that we'll explain. Chlorine 35 and 37. Now there's some big differences, right? We can do some rounding and say 75-25. Alternatively, if we want to just express that as a ratio, it's 3-to-1. Bromine 79-81, what's this ratio? So 1-to-1. Iodine, like fluorine, is 100%. So what is the point of belaboring this? We want to determine if any of those other heteroatoms are in a molecular formula. And those isotope ratios are going to tell us if they're there or not.
Why is protein and deuterium adding up to more than 100%?
Why is this adding up more to 100? More than 100? Probably a typo of mine.
And like the C14, like there is a natural balance between creation and decay. Otherwise carbon 18 doesn't work. Do we just neglect it?
So there is radioactive carbon on Earth, but it's in such a trace amount that relative to these two, we don't really need to quantify it. A lot of radioactive carbon is synthetically made, I think in Russia. But in terms of the distribution of naturally occurring isotopes, you know, if you went and dug up a soil sample, it's really, you're not really going to see it. So how can we use that information to determine if one of those heteroatoms is present? And again, you already know the answer to the question we're trying to solve here. How do we convert 288 into a molecular formula? What I want to do is go back and look at some of the data and rule out the other heteroatoms. So N, F, Cl, Br, and I. How can we rule those out? You know, oxygen is typically, because there's a lot of functional groups with it, it's typically present in a lot of molecular formulas. So what we're trying to do is rule out any of these other ones to validate our assumption that oxygen is present. And how can we rule these other ones out? Based on the isotope abundance of these, they're going to give specific signatures in the mass spec data that you kind of memorize or commit to memory based on the pattern or how it looks. You can say, okay, that is in there. And then once you know that, you can say it because it's this element, it's contributing this much mass to the molecular formula. So these have signatures that we can rely on in high confidence. Oxygen's the weirdo in that it's harder to determine if it's there. So we're going to look at these first. Then we'll get back into focusing on oxygen. And again, where we're going with that is once we make these assumptions and we say, okay, it's got 2 oxygens in the molecular formula, how do we know the bonding pattern? That's when we start using infrared spectroscopy to tell us it's an alcohol or a ketone or whatever. So these are the diagnostic signatures in a table form. We'll look at the data over the next couple slides. So here's our elements, the different isotopes, their masses, their abundance, and what is the effect on the mass data. If a molecular formula has an odd number of nitrogens present, the parent mass will be odd. If the parent mass is even, you could have an even number of nitrogens present. Then you're getting into even more murky waters at that point with your assumptions. How do we know if fluorine is present? That's tough to tell based on there only being one isotope, and it doesn't do anything to the data to tell us it's unique. Chlorine, because of that 3-to-1 ratio, 35 to 37. See this nomenclature here, M? That's your parent. See that, M plus 2. M will have chlorine 35. M plus 2 will have chlorine 37 because there's a difference of 2 in the mass units of those isotopes. So when you look at the parent region and find the M, you count over to the right 2 more mass units, you're going to see another signal. The ratio of those signals will be 3-to-1. It will stand out. bromine is a 1-to-1 ratio. So your M will have bromine 79. Your M plus 2 will have bromine 81. And you'll have two equal intensity peaks in that region. Iodine is not as bad as fluorine because sometimes you'll see the iodide ion at 127, or maybe there will be a fragment parent minus 127. So wherever your parent is, if you see some signal that's 127 mass units less, that's an indicator that iodine is in the molecule. So we'll look at these different heteroatoms and I'll point out the diagnostic signatures that you're looking for as to their presence, and then that's going to lead us back to this issue with oxygen. So this molecule is commonly known as aniline, otherwise aminobenzene. We saw the NH2 group, that's an amine. We can count the number of nitrogens, it's 1, that's an odd number. And so the parent here, let's say 93, so that's an odd number. So it's telling us there's got to be 1, 3, 5, 7, whatever number of nitrogens. So if I ask you a question, a compound gives a mass of 93, could you backtrack to that molecular formula? You would use the same thing, but now in this case you'd say, because 93 is odd, I'm going to assume there's 1 nitrogen. I can take 93, subtract 14, then whatever remains I'm going to assume is just C and H. Then from there you can determine the maximum number of carbons, hydrogens, and then get something that then fits in terms of a molecular formula. So fluorobenzene has an even mass, 96. There's the parent. So that's kind of tough to determine that fluorine is in there. There's nothing really diagnostic about it.
Would we be given the spectra, or just straight from the mass?
So again, I like to switch it up so I don't get bored writing questions. You'll either be given the actual spectrum or you'll be given a table of data. The table will show you the masses and the abundance that corresponds to each mass. So here's chlorobenzene. So look all the way to the right. So the molecular formula translated into the mass says the parent should be 112. So that's that tall signal. What else do you see when you count over? So if you count over 2, that's the M plus 2. So 112 plus 2, that's 114. So 112 is the parent. The parent plus 2 is 114. Visually, do you see that ratio? If you draw this line over here, that gets you to about 100. You draw this line over here, that gets you about 33. So there's your 3-to-1 ratio visually. So when you look at that, you can confidently say there is a chlorine in there.
You said earlier that the difference between the first parent ion and base peak were the neutral atoms that was being shown. Is that true for this too?
So in this spectrum, because the parent is 100% abundant, it is also the base peak. So if you really want to blow your mind, this is the spectrum for one chlorine. Now again, so that we're clear, maybe I'll draw this out, because this phenomenon is different than resonance. What this data is telling you, in the sample of this mass spectrum, there are 2 different compounds. Because chlorine has those 2 naturally occurring isotopes, you're seeing both of those compounds. One has the 35 label, the other has the 37 label. So that's a 3-to-1 ratio. And if you wanted to pep it up a bit, think about a molecule with 2 chlorine atoms. And what are the distribution of isotopes in a molecule with 2 chlorine? Because each can be 35 or 37. This parent will no longer look like that. It'll look pretty different. Here's bromobenzene. We see the parent for M is 156. Then we see that M plus 2 at 158. These are the numbers that you're looking for the ratios in parentheses here. See how that says 100 and that says 97.3? That's your 1-to-1 ratio. So to answer the question, you can either look at this data table you're given or visually inspect the parent ion region for that signature. Lastly, iodobenzene. The parent is at 204. There is a little blip at 127, so that would be an iodine cation or anion, depending on what mode the instrument's operating. But if you take 204 minus 70 or minus 127, you get that signal, 77. And that results from this molecule losing that iodine. So you can infer what is lost by the difference from the parent to the daughter. Questions? See if we remember some stuff here. So here you have the M and the M+2. And then the data you're given are the abundances. These are not the masses of those, just the abundance ratios. So which one of those is going to show the presence of bromine? So it's going to be C because that shows the 1-to-1 ratio. What about chlorine? So this will be A. I've made the math easy for you in that I've normalized it so it's easy to spot. But if the numbers aren't normalized, you have to do that yourself to determine that ratio. So which one contains a nitrogen? So B, that's the only odd one. So here's a challenge for you. We won't do it now, but see if you can figure it out. If you're given that mass, 45, so we know there's a nitrogen, can you take that and then determine a molecular formula? See if you can figure out, going through those steps, coming up with something that's reasonable. For a parent mass of 46 that contains 1 oxygen, what is the maximum number of carbon atoms that can be present? How'd you get that? Intuition. I believe you, but in terms of laying out the steps to arriving at that,
You subtract 16 from 46 to get rid of the oxygen, and then you figure out how many carbons you fit. It would still be 1 fit. So 46 minus 16. And then carbon being 2, you just subtract. What else was it? Yeah, and then you have 18 for that. And you've got space left for
for how many hydrogens?
yeah,
How many?
6.
So from the parent mass, and again, I've rigged the question in the sense that I'm telling you there's just 1 oxygen, so you know to subtract 16. And then we're making the assumption that everything left over is just C and H. So we want to determine the C count because that contributes more. We just do that maximum number thing, take the leftover, the 30, divide by 12. That's going to give us the maximum number of carbons. and then anything left is going to be hydrogen. Let me just state that, we're going to look at problems where I'm not telling you what other heteroatoms are in there or how many there are. That's when the IR comes into play. Those will have specific signatures that are telling you, okay, this is a carboxylic acid. Carboxylic acid has how many oxygens? It has 2. So now you know I need to take 16 times 2. So let's just flesh this out a little bit more. C2H6O. How many degrees of unsaturation does that have? How many?
0.
Has 0 degrees of unsaturation. Oxygen doesn't affect the hydrogen count, so we end up with C2H6. We compare that to the alkane molecular formula. So if we wanted to start drawing some structural isomers of C2H6O, what possible functional groups can we include that contain oxygen? Ether? So that would be an alcohol. That would be an ether. And I don't think we can propose any more from that. So those would be the 2. Then if you think about what is the difference, again, this has the OH, this does not. If you classify the carbons, sets of hydrogens, you'll come up with different responses. And then when we learn about NMR, you'd be able to look at NMR data and assign it to one of those pretty quickly based on those counts. About 3 minutes left. Let me see if I can get to this equation before we stop. So we looked at these different heteroatoms that were giving us unique signatures to tell us if they're there. But then oxygen was the weird one that we need to spend a little bit more time on to say, is it there or not? Because right now we're just making assumptions. Infrared spectroscopy will tell us it is there or it's not there. So as we saw in the prior problem, we were able to arrive at a molecular formula. From the degrees of unsaturation, we could determine what type of functional group the oxygen belonged to, and then we made some claims. So this last little bit, which we'll have to pick up on Wednesday, we want to follow that same logic that we started the lecture with, of given that mass, how do we figure out the carbon count? We already know there's some oxygens in there, but the way we started with dividing by 12, you'd be hard pressed to come up with a ratio that has oxygens in there. So this equation here is what you use to find the exact number of carbons. And the reason this works is because of that isotope abundance of C12 to C13. If we just say that C13 is about 1.1% abundant, the implications of that is for any molecule randomly distributed, there's going to be a C13 in there. And because 13 is one more than 12, your parent is going to have an M+1 signature to it. And depending upon the number of carbons in there, the abundance of that M+1 will increase. So you can take your abundance numbers of M+1 divided by M and then divide all that by 1.1. That tells you the exact number of carbons. So you don't have to go through this, what's the maximum level? It tells you the exact number. So we'll pick that up on Wednesday, then we'll run back through the testosterone data and arrive at its MF.